Hi everybody. So in this video we're going to be covering another topic under Chapter 1, Number and Algebra Basics. And in this case, it's going to be 1.2, the exponent laws. So here we have a summary of the exponent laws. Now one thing that is very important to point out is that these laws only apply to cases where you have the same base. So you'll notice that all these examples have the base A. Okay, so the first law says that if you have the same base as multiplying, that the result of that multiplication will be having that base and adding the exponents. The next law, law number 2, says that if you have a number like a to the m, and that is elevated to the power of n, then that equals a to the power of m times n. The exponent law 3 says that if you have two numbers multiplying, like a times b, and they are both to the power of n, then that is the same as saying a to the n times b to the n. In similar manner, if you have a divided by b, or a over b, to the power of n, that is equal to a to the n over b to the n. And notice that next to that, in the definition, it says b cannot equal 0, obviously because you cannot divide by 0. Then again, if you have a to the m over a to the n, and this is exponent law number 4, it says that this equals a to the power of m minus n. So in multiplication, we would add the exponents, and in division, you will subtract the exponents. Again, remember that the base must be the same. The exponent law number 5 says that if a is to the power of a negative number, like a to the minus m, that is equal to 1 over a to the m. So this is a reciprocal, 1 over a to the m. Exponent law number 6 says that if you have a to the power of 1 over m, that is equal to the mth root of a. So this is a rule, exponent rule, for roots. Then if you have a to the power of n over m, that is the same as saying mth root of a to the power of n, or this is the same thing, a to the power of n under the mth root. Okay, so in the next slide, you're going to see example 1.10, and it says evaluate. So example A says 2 to the 3. Now remember that this is simply 2 times 2 times 2, 3 times, which is 2 times 2, 4, times 2, 8. For B, we have that they want us to find the answer to negative 3 squared. Now here you have to be careful because this expression is not the same as this one. These are different. This will always give you positive because if you have negative 3 times negative 3, that is going to equal positive 9. Whereas this means negative 3 squared, and this is going to be negative 9. You can prove this very easily with your calculator. For C, we have 2/3 to the power of 4, and that's just going to be 2 to the 4 over 3 to the 4, or 16 over 81. Okay, so now we have example D, and it says, what is minus 0.2 to the power of 5? So this is simply going to be minus 0.2 times 0.2 times 0.2 times 0.2. This is 1, 2, 3, 4. One more times 0.2. And this is going to equal negative 0.00032. Very well, so next we have example 1.11, and it says for part A, write 3 to the 4 times 3 to the 2 as a single power. So that's simply adding the exponents. So this is going to equal 3 to the 6. For part B, it says use the repeated multiplication model of exponents and show that a to the m times a to the n equals a to the power of m plus n, where m and n are positive whole numbers. Okay, so for B, we could say this. If we have a to the m, we know that that equals a times a times a times a, and this is going to be m times. Then if we have a to the n, we know that this equals a times a times a times a n times. Okay. Therefore, if we have a times a times a, etc., and this is m times, and this times a times a times a times a, etc., and this would be n times, then we know that this has to equal a to the power of m plus n. Okay, so next in the video is example 1.12, and part A says simplify 5 to the 4 squared. So recall that the rule here is to multiply the exponents, right? So this would be the same as 5 to the 8. So B says write the number 64 as a power in as many ways as possible. Okay, so for this exercise, what I would recommend you to do is to grab 64 and factor it, right? Find its prime factor. So always start by dividing by 2 if you can. So you divide by 2, and this will be then 32. Divide by 2 again, you get 16. Divide by 2 again, you get 8. Divide by 2, and you're going to get 4. Divide by 2, you get 2. Divide by 2 one more time, and this is going to be 1. So notice that we have 2 repeated here several times. We have repeated 1, 2, 3, 4, 5, 6 times. So that means that 64 is the same as saying 2 to the power of 6. What other combinations can we make? Well, notice that if we have 2 times 2, 2 times 2, and 2 times 2, that's 4. And 4 to the power of 3 would then be also 64. We can also group them in threes. Notice that if I group 2 times 2 times 2 and 2 times 2 times 2, that's going to be 8 times 8, or 8 squared. Finally, every number to the power of 1 equals itself. So we can also say that we can write 64 as a power as 64 to the power of 1. Okay, so now for part C, they're asking us to show that any number that is a power with exponent 6 is a cube and a square. Interpret this result geometrically and give a numerical example. Okay, so what does this mean? What this means is that if you have any number, let's say a number a to the power of 6, it can either be a cube or a square. Well, this is easy to see because this is the same as saying a squared to the power of 3. So this is a cube. They say interpret this geometrically. What does it mean? Well, if we have a cube, we can draw a sort of cube here very quickly. This would mean that we could find the volume of the cube by cubing a squared. That means that a squared is the lengths of the edges, right? So every edge of the cube is the same. So this would be a squared, this would be a squared, and also the depth would be a squared. We can also write a to the 6 as a cubed squared. So that means that we can think geometrically of a square that has side lengths a to the 3, whatever a to the 3 is. Because this would be the same, the area of the square would be a to the 3 squared. Then it says that we need to give a numerical example. Okay, so let's suppose that a equals 2. So notice that if we have 2 to the power of 6, we can write that as 2 to the 2 cubed. And this is going to be 4 cubed. So that means that in this case, we would have a cube that has a side length of 4. So the cube would have 4 as the length of its sides or edges. And then likewise, if we have 2 to the 6, we could rewrite that as 2 to the 3 squared, which is the same as 8 squared. So that would mean that we would have a square that has side lengths that measure 8. Okay, so next we have example 1.13, and part A says write 5y cubed as a product of power. So that's simply saying that 5y cubed is the same as 5 to the 3 times y to the 3. For part B, they ask us to verify that a times b to the n is equal to a to the n times b to the n is true by using 15 squared and 3 squared times 5 squared. Okay, so what we have to verify is that 15 squared is the same as 3 times 5 squared, which is same as 3 squared times 5 squared. So 15 squared is 15 times 15, which is going to be 225. And then 3 squared is 9, and 5 squared is 25. But 9 times 25 is also 225. Part C says use the same fact, right? That a times b to the n equals a to the n times b to the n to find the prime factor decomposition of 12 cubed. So what we need to do is factor 12, like I showed you before. Always start with 2 if possible. So 2 times 6, 2 times 3, 3 times 1. That means that 12 is equal to 2 squared times 3. But in this case, it's 12 cubed, so it would be this cubed. And this is equal to 2 to the 6 times 3 cubed. Then our next example is 1.14. And part A says, show by choosing values for a and b that a plus b squared is not equal to a squared plus b squared. Now this is a big no-no, and this is a very common mistake that students make. They assume that if you have a plus b squared, that equals a squared plus b squared. That is probably because this is confused with the rule that is actually true, which is that a times b squared equals a squared times b squared. Now this is true, but this is not, and we're going to use a counter example. That's what this is called. If you have just one example that proves this wrong, then the rule would be wrong in general. So if we have a equal to 1, for example, and b equal to 2, then we would have 1 plus 2 squared, and let's assume it's true, is equal to 1 squared plus 2 squared. 1 plus 2 is 3, so this would be 3 squared, and then 1 squared is 1, and 2 squared is 4, so this is 1 plus 4. Now notice that obviously 9 is not equal to 5, therefore this is false, and so is this, forever and ever false. So please don't fall into that common trap. Now they say by expanding a plus b times a plus b, show that a plus b squared is equal to a squared plus 2ab plus b squared. So the thing is that a plus b squared is really equal to a plus b times a plus b. So if you multiply these, remember that you have to do distributive property. You have to distribute a and multiply it by a, and then multiply it by b, and then you have to do the same thing here, multiply it by this and multiply it by that. Some people like to write it like this. They say that this is the same as a times a plus b times a plus b. Okay, and this is going to equal a squared plus ab plus, and although this is b times a, always write in algebra the letters in alphabetical order. So this would be the same as A times B. And then this plus B squared, and this is obviously going to be A squared plus 2AB plus B squared. Okay, so now we're going to do part C. Okay, so for part C, they're saying use a counterexample to conclude that for n greater than 2 and ab not equal to 0, a plus b to the n does not equal a to the n plus b to the n. So this would be to discard for other values that are greater than 2. So let's choose n equal to 3, a equal to 1, and b equal to 2. So we would say that a, and we're going to assume it's true, right? So 1 plus 2 to the 3 equal to 1 to the 3 plus 2 cubed, or 2 to the 3. Okay, so this is going to be 3 cubed. We're going to end up getting 3 cubed. And this is going to be 1 plus 8. And 3 cubed is 27, which is obviously not equal to 9. So that means that all this is false. Therefore, we have used the counterexample appropriately. Very well, so this is now example 1.15, and it says write each quotient as a single power. So A says 3 to the 6 over 3 to the 2. So let's recall the rule. The rule was opposite to the one of multiplication, where we added exponents. And here, in this case, we subtract. So this is the same as 3 to the 6 minus 2, or 3 to the 4. For B, they have x to the 9 over x to the 7, and this is just going to be x squared. For C, they have something a little bit different. For C, they have 4 to the 9 over 2 to the 6. So we cannot just go 9 minus 6 because we need to have the same bases, or all the exponent rules don't work. But 4 is the same as 2 squared. So 2 squared to the 9 over 2 to the 6. So this is going to be 2 to the 18 divided by 2 to the 6. And now we simply subtract the exponents, and we're going to get 2 to the 12. D is 8 to the 5 over 8 to the 5. Now notice that this is interesting because you could just cancel out and get 1 right directly. But you can also write this as 8 to the 0. And this is equal to 1. This is where that rule, that general rule that says that any number to the power of 0 equals 1. This is why. This is why it is, as you can see it in this example. Then we have for letter E, 3 squared over 3 cubed. And this is 2 minus 3, so it would be negative 1. So this would be 3 to the minus 1. So next we have example 1.16, and it says write each of these powers using positive exponents and evaluate where possible. Okay, so for A, we have 3 to the minus 2. So we know that this is the same as 1 over 3 squared, and this is 1/9. For B, we have 4 to the minus 3. We do something very similar. We just go 1 over 4 to the 3, or 4 cubed, and this is going to be 1 over 64. For C, we have a fraction, or a quotient, 1/2 to the power of negative 1. With fractions, all we have to do is flip them around. So this is the same as 2 over 1 to the 1, and this would then equal just 2. For D, we have 3x, or 3x to the minus 4, actually, 3x to the minus 4, and this squared. So remember that we apply the rule where we multiply the exponents of the numbers or letters inside the parenthesis. So this would be the same as 3 squared times x to the power of negative 8. But 3 squared is 9, and then because this exponent is negative, we could just write that as 1 over x to the 8. And then this is simply 9 over x to the 8. And finally, we have example E, where they have x to the minus 1 times y to the 3, and this to the negative 2. So what I would suggest you do is multiply the exponents first, and you're going to get x squared times y to the negative 6, and we can just rewrite this as x squared over y to the 6. Now notice that we cannot simplify the exponents or do anything with the exponents here because these are different bases. Very well, so now we are on example 1.17, and it says for part A, write each of these powers using roots and evaluate. Okay, so for roots and powers, we have to have one thing very clear, because this is probably the most confusing rules of powers for most students. So if you have a number a to the power of 1 over n, this is equal to the nth root of a. Example, if you have a to the 1/2, this is the square root of a. Remember that the square root implies that you have a 2 here. You just don't write it because square roots are so common. If you have a to the 1/3, this would be the cubic root of a, and so forth. Now, if you have a to the power of b over n, then this is equal to, again, the nth root of a, but all of this to the power of b. Now, we can see that this is true very easily because this is the same as writing. Notice it's the same as saying a to the 1 over n to the power of b, right? So it would be the nth root of a to the b. Or what can say the same, but the opposite, right? We could say that this is the same as saying, right? A to the power of b over n is the same as saying a to the b to the power of 1 over n. So this is the same as a to the b, and on top of that you have the nth root. Okay, so these are the rules, and now we're going to apply them to solve these problems. Very well, so with a, we have part 1, and it says, what is 16 to the 1/2? So we know that this is simply the square root of 16, and that is 4. For number 2, we have 27 to the 1/3, and this is simply the cubic root of 27, and this is going to equal 3, because 3 times 3 times 3 is 27. Next, they have 64 to the power of 3/2. So remember that this is the exponent, and this is the root. So this, we can rewrite this as square root of 64, and this to the power of 3. And this would be the same as 8, because the square root of 64 is 8, as 8 to the power of 3, and that's 8 times 8 times 8, which is 512. Okay, so for B, we have the question, for which values of n is n to the 1/2 undefined? Or actually, no, defined. Okay, so n to the 1/2, remember, is the same as the square root of n. So remember that we don't have square roots of negatives. Therefore, n has to be greater or equal to 0. That would be the values for which n to the 1/2 is defined. Any value greater or equal to 0. Now, why is that? Well, because if you have square root of -4, that does not equal -2, for example, right? Because -2 times -2 is +4. So that means that for any even root, so for example, if you have the fourth root of -16, this has no solution. You can plug any of these numbers in the calculator, and you're going to get an error because there's no solution. But what happens if you have an odd number? Well, odd numbers do work, because if you have the cubic root of -8, that does equal -2. Why? Well, because -2 times -2 times -2 is equal to -8. So there is a number that multiplied by itself gives us -8. And the same would happen with all odd roots. Then they say in the other part, what about -1 to the power of n? So I'm going to do that over here. So if we have -1 to the power of n, n can be any integer. So if n can be any integer, right? Because -1 to the power of 3 is -1, -1 to the power of 4 is 1, and so forth. But what happens if we have a fraction? Let's suppose that n is equal to a fraction a over b. Then -1 to the power of a over b would not have solutions, no solutions when b is even. Now, what does that mean? Well, let's suppose we have -1, the square root of -1, or actually, let's say -1 to the power of, say, 1/2, right? Then this would be the same as square root of -1, and this has no solution, no real number solution. Even if we have -1 to the power of, let's say, 5/4, remember that this would be the same as or the fourth root of -1 to the power of 5. Now this in here would have no solution. Therefore, there is no solution at all. Okay, so for part C, they're saying solve. And the first one they want us to solve is p to the power of 2/3 equals 25. Okay, so how to solve these exponent problems? There are many different ways to solve them. I'm trying to do it in the simplest possible way in order to not cause any confusion. Okay, so let's think of it this way. Remember that I could rewrite this p to the power of 2/3. I could write this as p to the 1/3 squared. Now, why do I want to do that? Because I want to compare it to 25, which is the same as 5 squared. Because this is squared and this is squared, it implies that p to the 1/3 is equal to 5. Now, but they're not asking us to solve for p to the 1/3. They want us to solve for the variable p. But we can do a trick here. Now, notice that if I multiply this exponent by 3, I'm going to get p to the 1, or p. But if I do it on one side of the equality, I have to do it to the other side. So then I would have to elevate this to the power of 3. So that means that p is equal to 5 cubed, and that is just 125. Now you can verify that with a calculator by plugging in 125 to the power of 2/3, and you will see that it gives you 25. Then they want us to solve for p as an exponent. So we have 49 to the p is equal to 343. So the trick with these exponential problems is that we get the same base on both sides. So if you factor 343, you're going to see that it's divisible by 7, not by 2 or by 3 or by 5, and then you get to 7. And you're going to see that it's the same as saying 7 times 49. And then this is divisible by 7 again, 7 times 7, and 7 times 1. Okay, and notice that 49 is 7 squared, so we can write this as 7 squared to the power of p is equal to 7 cubed. But this is the same as saying 7 to the power of 2p is equal to 7 cubed. Once we have this situation where we have the same base on both sides, then what we really have to solve is simply 2p is equal to 3. Therefore, p is equal to 3/2. So example 1.18 is the last one on this video. For A, they ask us to find or to simplify the expression x squared to the power of 3 times x to the minus 1 to the power of 0 over x squared times x to the 1/2. So we simplify by applying the rules for exponents. So This is going to be x to the 6 times x to the 0. And this is going to be x to the 5 halves, right? Because 2 plus 1 half is 5 halves. But x to the 0 is 1. So this is simply x to the 6 over x to the 5 halves, which is the same as saying x to the 6 minus 5 halves. And you're going to get that this equals x to the power of 7 halves. Then we go with b. And then for b, we have 2 to the 6 times 4 to the negative 1 over 16 to the 1/4 times 32. Okay, again, there's several ways of doing this. You can pick your own way if you know alternative ways, but I'll do it this way. The first thing I'm going to do is that I'm going to change everything to the same base. Now, all of these numbers have obviously a base 2, like 4, 16, and 32. So we can rewrite this as 2 to the power of 6 times 2 squared, which is 4, times negative 1. That would make it 2 to the negative 2. And then 16 is 2 to the power of 4. So let's just write it so we can see it. So this is 16 is 2 to the power of 4, and this to the power of 1/4 times 32, which is 2 to the power of 5. Okay. So notice, first of all, that 4 times 1/4 cancels out because 4 divided by 4 is 1. So this is just 2 to the 1. This up here, we're going to add the exponents. So 6 plus negative 2 is 4. So we get 2 to the 4. And then here we're going to get 2 to the 1 times 2 to the 5. That's going to be 2 to the 6. And we can subtract either way, right? If I go 4 minus 6, I get negative 2 on top. Or I can go 6 minus 4 and just have 2 on the bottom. So I'm going to go 1 over 2 squared. So this is equal to 1/4. And finally, for c, we have x squared over y to the minus 3. And all of this to the power of negative 2. Again, several ways of doing this. You can choose your own. What I'm going to do is simply multiply the bases from the quotient by negative 2. So I'm going to get x to the minus 4 over y to the 6. Y to the 6. We can rewrite this as 1 over x to the 4 times y to the 6. Now remember that these are different bases, therefore we cannot add the exponents.